Assalamualaikum and a very good day to everyone. We are from Group 6. We'll be presenting the topic Neutron Detector. But before we start, let's get to know our members. Our group consists of me, myself, Siti Nurain binti Ahmad Razwanuddin, Nurul Anis Nabila binti Muhammad Yusri, and Manisha binti Harun. Alright then, let's start, shall we? What is neutron detector? It is a specialized device used to detect and measure the presence of neutrons, subatomic particles that have no electrical charge. Neutron detectors are designed to detect neutrons and provide information about their characteristics, such as energy, intensity, and directions of travel. In 1932, James Chadwick discovered the neutron as a neutral subatomic particle. Shortly after the discovery, James developed the Chadwick counter. It used a gas-filled cylindrical tube with an entrance window which allowed neutrons to enter and collide with the gas atom, producing ionization, which indicating the presence and intensity of the neutrons. In 1940s, scintillation detectors emerged as an alternative method for neutron detection, in which the use of scintillator materials that emit flash of light upon interaction with the radiation are adapted. Neutron detectors continue on developing as in 1950 as proportional counters based on the principle of gas ionization become popular neutron detectors in which they are utilized a gas-filled chamber, often with a mixture of helium and proportional gas like argon or methane. In 1960s, detectors based on specific isotopes with a high neutron capture cross-section gained prominence, boron-10 and lithium-6. Starting in the 1970s, detectors based on the isotope helium-3 gained popularity for neutron detection due to their high efficiency and sensitivity. Until then, the field of neutron detection continues to advance with ongoing research and development aimed on improving sensitivity, efficiency, and portability. Neutron detectors have been used widely in our industries, such as in hazardous gas detections, where neutron detectors are used to detect the presence of hazardous gases such as methane, carbon monoxide, and sulfur dioxide, where these gases are dangerous to human health and safety. Next, oil and gas industry, where neutron logging tools use neutron detectors to measure the presence and distributions of hydrogen atoms in the formations. Next, quality control, where neutron detectors are used to monitor the quality of products such as food and beverage. And lastly, the radiation therapy and medical imaging, where they utilize neutron detectors to visualize the internal structures of objects, including biological samples and industrial components. Neutrons are neutral particles, so they don't interact with the electric fields. This means that they can be detected with traditional charged particle detectors like Geiger counters. Neutrons can be detected by their interaction with other nuclei. When a neutron collides with a nucleus, it can be either be absorbed or scattered. If the neutron is absorbed, the nucleus will become radioactive and emit gamma rays. If the neutron is scattered, it will change the directions and lose some of its energy. Neutron detectors employ various mechanisms to detect and measure neutron interactions, such as gas ionizations. Neutrons interact with the gas atoms inside the detector, causing ionizations or excitations. The resulting charged particles, electrons or ions, can be detected and measured. Next, scintillation. Neutrons interact with the scintillator materials, leading to emissions of flash of lights. Photodetectors capture and convert this light into electrical signals. Lastly, solid-state detectors. Neutrons interact with the semiconductor materials, producing ionizations or nuclear recall events. These interactions generate electrical signals that can be detected and measured. Neutron flux and intensity are two important concepts in neutron detections. The neutron flux is a measure of the number of neutrons present in a given area, while the neutron intensity is a measure of the rate of which those neutrons are moving. In neutron detectors, the neutron flux is typically measured by counting the numbers of neutrons that are detected over a period of time. The neutron intensity can then be calculated by multiplying the neutron flux by the neutron velocity.
Working principle of neutron detectors. Neutron detectors consist of materials that interact with neutrons. Although the principal reaction mechanisms of neutrons with matter are limited, the options for detection media are quite numerous. Detectors can consist of solid, liquid, or gas-filled media. Besides the detection mechanism, there is one major challenge for all types of neutron detectors. They all need to be insensible to gamma ray emission, or at least require an implemented technique to discriminate between neutron and background gamma ray events, as neutron detection often takes place in a mixed radiation field. Here are some of the properties of a neutron detector. First is the sensitivity. The sensitivity of a neutron detector is its ability to detect neutrons. Then, resolution. The resolution of a neutron detector is its ability to distinguish between different types of neutrons. Next is background. The background of a neutron detector is the amount of noise that present in the detector signal. And lastly is the energy range, which is the energy range of a neutron detector is the range of neutron energies that the detector can detect. There are two basic types of neutron interactions with matter are available. First is scattering. The neutron can be scattered by a nucleus, transferring some of its kinetic energy to the nucleus. If enough energy is transferred, the recoiling nucleus ionizes the material surrounding the point of the interaction. This mechanism is only efficient for neutrons interacting with light nuclei. In fact, only hydrogen and helium nuclei are light enough for particle detectors. Second is nuclear reaction. The neutron can cause a nuclear reaction. The product of these reactions, such as protons, alpha particles, gamma rays, and fission fragments, can initiate the detection process. Some reactions require a minimum neutron energy, which is the threshold, but most take place at thermal energies. Detectors exploiting thermal reactions are usually surrounded by moderating material to take maximum advantage of this feature. Here are two main types of neutron detectors. The first is scintillation detectors. It uses a scintillating material that produces light when it is struck by a neutron. The light is then detected by a photomultiplier tube, which converts the light signal into an electrical signal. The second neutron detectors is gas-filled detectors, which is it uses a gas that is ionized by neutrons. The ions are then detected by an electric field, which produces an electrical signal. Now let's move on to the working principle of scintillation neutron detector. First, a neutron strikes a scintillating material such as boron-10 or lithium-6. The scintillating material then produces light when it is struck by a neutron. Then, the light is detected by a photomultiplier tube, which converts the light into an electrical signal. Lastly, the electrical signal is amplified and processed to produce a readout of the neutron count. Next is the working principle of gas-filled neutron detector. A neutron strikes a gas, then the gas will ionize by the neutron. The ions are detected by an electric field, which produces an electrical signal. Then, the electrical signal is amplified and processed to produce a readout of the neutron count.
Now, we have learned about two types of neutron detector, which are scintillation detector and gas-filled detector. Let's see the applications for both neutron detector in industry and its benefits. Scintillation detectors are used in a variety of industrial applications, but in this video, we will focus on medical imaging and oil and gas industry. The first one is medical imaging. This detector is used in medical imaging equipment like single photon emission computed tomography SPECT and positron emission tomography PET scanners. Both of these equipment are used to detect the radiation emitted from radioactive materials that have been injected into the patient's body. For example, The SPEC scanners using a gamma camera. The camera has scintillation detector, which is a crystal that emits light when exposed to radiation. An electrical signal is then generated from the light using a photomultiplier tube (PMT). The computer then generates a 3D image of the body using the signal that the PMTs have amplified and transmitted. SPEC is used to diagnose a variety of medical conditions, including heart disease and cancer, and help to improve the quality of life for patients. The second application is in oil and gas industry. To explore petroleum, this detector identifies the presence of radioactive materials in the earth. The radioactive elements in the ground emit gamma rays. The intensity of the gamma rays can be used to determine the concentration of radioactive elements in the ground. It is possible to locate possible oil and gas resources using this information. Gas field detectors are also used in a variety of industrial applications, but in this video, we will focus on hazardous gas detection and food quality control. The first one is hazardous gas detection. Hazardous gases like carbon monoxide can be found using these detectors. To make the detector work, the gas molecules inside the detector are ionized, which results in the production of an electron and a positive ion. Electrodes in the detector then gather these charged particles, generating an electrical current. The strength of the electrical current is proportional to the concentration of the gas in the air. This current can then be used to indicate the presence of the gas. It's critical to be able to identify these gases in the workplace, since they can pose a risk to worker health and safety, such as at factories and schools. Hence, it will help to protect people from exposure to harmful gases. The second application is food quality control. This detector can be used to monitor the quality of products and detect the presence of contaminants in food and beverage products, such as bacteria and pesticides. They aid in ensuring that goods are both safe to use and fulfill the necessary quality standards. In this field, the detector works the same as hazardous gas detection. In the case that the amount of bacteria is more than a standard level, the detector will sound an alarm. As a conclusion, a neutron detector is a specialized device used to detect and measure the presence of neutrons, non-electrical subatomic particles. It provides information about neutron characteristics such as energy, intensity, and direction of travel. The main challenge for all types of neutron detectors is to be insensible to gamma ray emission or require an implemented technique to discriminate between neutron and background gamma ray events. In general, neutron detectors provide information only on the number of detected neutrons and not their energy. There are a variety of industrial applications that use neutron detector to help them handling and facing the working environment efficiently, since it is very sensitive to neutron and reliable to be used in industrial environments.